before that, yes, maybe that was supposed to be presented before. I want to tell you that there are 4 control rods of equal reactivity worth. When I mean reactivity worth means the neutron absorbing capability power of each rod is exactly the same. Because in the main reactor, which is the father of that reactor, we had different reactivity worth in each rod. There were some coarse rods which had bigger ability to absorb neutrons than the fine. But here we decided to have just all of them with the same reactivity worth. The stepping motor, which moves up and down the rods, has a resolution 0.02 millimeter per step, which is very accurate. Every step we send, because the programming controller, as I told you a little while ago, sends number of steps to the motor. And every step causes the motor to go in only 0.02 millimeters, which is very good resolution for the rods. The safety. We've been concerned, of course, with the safety, and we decided, because to shut down a nuclear reactor is a hassle. I mean, if there's not very good reason to shut it down, don't do it, because we know very well if the reactor stays more than half an hour shut down, the poison started being created, and this poison reduces the reactivity, and you have to introduce new reactivity to the reactor to start it. So we don't want, without reason, to do that. So we said that no single failure, which means, I'm going to tell you later on, what I was supposed to have told you, that some critical instrumentation has been duplicated or triplicated. So, and we postulate that if there is a single failure of an instrument, which doesn't impose, we don't want to impose shutdown of the reactor, we don't do it. So we say no single failure will impose the operation. Critical instrumentation must be duplicated or triplicated. And only a double failure, which means 2 controller rods, or if 2 instruments out of the 3 or out of the 2 fail, then we shut down the reactor. And the controller is duplicate and redundant. By redundant, I mean that the same part of the algorithm runs at the same time within the programming controller. And if one programming controller for a certain reason goes kaput, the other one takes over and continues without showing the interrupt. And the cycle, when I mean the cycle, the algorithm goes in an infinite loop every 200 milliseconds, which means in every 200 milliseconds, the algorithm reads all the inputs from the field, does all the calculation, and outputs the, don't laugh, bugger, and outputs to the field. Also, we took into consideration something which, okay, if one controller fails, the other one is there to watch that the controller failed and takes, but if both controllers fail, what is going to happen? No one is going to be there to catch the error, so we have some watchdogs. This is not any dog, but it's an external hardware which watches both programming controllers. If both of them go kaput, the watchdog takes over and shuts down the reactor. This is for safety reasons. And now I go to my last step, last but one, because it will be the algorithm. So the algorithm is just a flow chart. Not as a flow chart, it's just a pseudocode of the algorithm. What the algorithm starts when the reactor comes on and the software starts running, it checks the status of the rods to see, is the rod available or unavailable? Is the rod frozen somewhere, is stuck or whatever? Yeah, you know that. So if 2 rods are unavailable, because we said before double failure is going to shut down the reactor, we shut down the reactor. Yes. That's good signal. I put some. If one has failed, then the control with the other 3. I go a little bit fast now. Then we check the RPS, the reactor protection system, if it has trip. If it has trip, well, we don't have backup to take over, so we shut down the reactor. Then we check the instrument nationality, the instrument from the fields. If the instrument is redundant and one has failed, we use the other signal. If both signals fail, we don't have another one, we shut down the reactor because we don't have feedback. But in case we have some signal, we select the rational of the two. Then you use the thermal variables to calculate the thermal power. The thermal variable is the chimney temperature, the bypass, the secondary, and the flow. Then we read the operator set point, what power he wants. Then we read the neutron power from the fission chambers. Then what happens, we log the thermal power, because we know if there is a power coming up, the neutronics is going to catch it right away, because this neutron are reacting very fast, but the thermal is going to take about 200 seconds to reach. So we have to take it back, to interpolate, in order to make it the same instance of time. Then we have to compare the two powers, the thermal and the neutron. And there is discrepancy because they're supposed to be the same, we shut down the reactor. Then we get the error, the logarithm of the demand power to this. This should be the same. So because the demand power, the reaction should be the same. So this should be 1. If it is not 1, we know that there is a discrepancy. So automatically what we do, we send the V1 is a variable which is going to be between -1 and 1, and it's going to be positive or negative according if the one power exceeds the other. And by that way, we send to the rod number of steps upwards and downwards. And because the time runs, and somebody give me signals, but I'm yapping a lot. So I go to the conclusion. They say that system has been designed already, and all documents have been issued. Has not been implemented, of course. The test of the control rod mechanism, we are going to simulate on one loop, not 4 of them, has been prepared and is going to be carried out at Spell Lab in Sheridan Park. The simulation of the reactor system is on development on the AT computer, and using that simulator as an overall, we'll test all the blocks of the algorithm, the one I showed you a little while ago, and that test is going to be performed in the Chalk River National Laboratories. So I finish here, and I wish you Merry Christmas. Happy New Year. Happy Hanukkah, excuse me. I forgot.